Okay, hi everybody. We're going to go over section 5.3, some notes, and discuss a little bit about friction and types of friction. So far, we've run into friction and really haven't had to break it down for any reason yet. We know that it's caused by two surfaces in contact, and it's an opposing force, but other than that, we haven't really spoke a whole lot about it. But speaking of the opposing force thing, it always acts opposite of the direction something's moving or trying to move, or actually, let's say sliding or trying to slide would be a better way. So right now I have up the notes, and I'm going to flip back and forth to some basic examples using some objects on my tabletop here. So there's two general types of friction. They're known as static and kinetic. There's also rolling friction, which I'll kind of talk a little bit about at the end. And rolling friction could take possibly characteristics of either of those in the right situation. But we're going to focus mainly on the two called static or kinetic friction. And symbolizing them, you can see here in our notes, FFS for static friction and FFK for kinetic friction. Sometimes your book just uses FS and FK like that, but usually I'm using kind of like the big F and the lower subscripts like I usually do for forces. Alright, so with the two types of friction, I'm actually going to go to static friction first, but actually the next thing I'm going to discuss is really about both of them to decide what makes up friction. What factors basically cause friction to be higher in one scenario and lower in another scenario. So the first example, and you guys that aren't in class could do this with me. I just want you to clear up a space on a table or desk in front of you, and I want you to put your hand just setting on the tabletop, not pushing on it or anything, just how it just naturally lays. I want everybody to just slowly pull your hand across the table towards yourself. Alright? So obviously your hand was a sliding object while doing that. And there's friction involved. You could literally feel the friction between your hand and the tabletop. And just to help us get some ideas about what can make friction higher, the second thing I want you to do is to put your hand out again, but this time push it as hard down as you possibly can and pull it towards yourself again. You should feel a lot more friction this time, right? So that gives us a look into what possibly causes friction to be higher. Think about what I just did right there. I pushed down hard, right? And let's take the normal force idea. Remember, the normal force, even if my hand's just laying here, the normal force of the table has to push up perpendicularly on my hand. So I'm pointing upward like the normal force would right there, right? Straight upward, okay? And if my hand had a weight, as far as the table's concerned, of 10 newtons, then the table has to push back on my hand at 10 newtons. Right? That's all old stuff we should remember. But when I push down harder the second time, the table thinks my hand's heavier. The table doesn't know any better, right? So if I push real hard with my hand on the table thinks there's a heavier object on it, right? So it's got to push back even more. And that interaction between a greater normal force of me pushing down, or essentially making my hand feel heavier, and the table pushing back, forces my hand and the table to be together with more pressure between them, essentially. And that causes friction. That's one thing that causes friction to be greater. So normal force is one of two big factors that causes friction to be bigger or less than in the right scenario. The greater the normal force, the greater the friction, regardless of the type of friction we're talking about, static or kinetic or even rolling. Okay? But there's another big factor as well. And this factor I did not change in both cases of pulling my hand towards me when it's just sitting there as opposed to pulling it hard. I kept this next factor I'm talking about, I kept it a constant. because in both cases, one of the surfaces was my hand, the other was the tabletop. And that didn't change either way. Now this would be a different amount of friction. If my tabletop was sandpaper, I probably wouldn't want to push down on it as hard as I could and pull it towards me, because that amount of friction would start hurting my hands, right? But that tells me something. The texture of the tabletop or my hand, or a combination of both, definitely comes into saying how much friction there is involved in calculating it. We call that, we give it a name called the coefficient of friction. I'm going to flip back to the notes here for a sec. In the notes, I'll just find the symbol somewhere. Right here's the symbol. It looks like a cursive U when handwritten, okay? And it's actually the Greek letter lowercase mu. That's mu. And it stands for the coefficient of friction. The coefficient of friction is the amount of roughness or smoothness between the two surfaces involved. Okay, and it's one of the few values we have run into in mechanical physics that is unitless. And here's a conceptual reason why. Think of it like as somebody saying, on a scale of 0 to 1, how rough or smooth are the surfaces in contact with each other? Okay, so it's like a scaled value in that kind of conceptual sense, okay, where any mu values, coefficients of friction closer to 0, would be two very smooth surfaces. Okay, any mu values closer to 1 are going to be really rough surfaces in contact. Okay, now it is possible to get mu values over the value of 1 in extreme cases. Most of the time, though, we don't see too often mu values going over 1. I don't want to say they can't, but most of the time they don't. So when it's time to solve for a mu value, if you don't get between 0 and 1, I'd be probably pretty concerned that whether I did the problem right or not. And mu can't be negative, because remember, it represents the roughness or smoothness of the surfaces in contact. It wouldn't make sense to be negative based on the nature of the idea of coefficient of friction. And it actually can't even be 0, because if you really have two surfaces in contact, all right, then you're going to have at least some friction. It might be really low. It might be real low, like a hockey puck on ice. It's very low. It wouldn't be nothing, though, okay? Because the origin of friction, since we now know it's dependent on the texture and the normal force of pushing those surface pushing back on the other object, microscopically, if you could see a surface you wouldn't think smooth, like this tabletop feels very smooth, right? Microscopically, though, if you look very closely, even the surfaces that feel smooth are very bumpy, okay? And those bumps locking together with the bumps on the other surface is really what creates the friction. That's the origin of friction. And it makes sense then, since more rough textures have more bumps to dig in, basically, essentially, to the other objects, that's a factor with how much overall friction there is, and how the normal force between the two surfaces pushes those little tiny bumps together in order to create more or less friction, depending on how much of it there is. So the two big factors are friction, for creating friction, either type, static or kinetic or even rolling, are mu, the coefficient of friction, and the normal force acting between them. All right, so that's the conceptual idea. Now, I want to throw in another example here, though. Some of us may have seen simple demonstrations like this, or even more complicated ones with maybe like a entire tablecloth. But to get the idea on the camera in here, just a small idea, I have a sheet of paper underneath my block here, okay? And if I pull the sheet slowly, there's obviously a decent bit of friction between the block and the sheet of paper because it's pulling the block along with it. But if I really quickly pull this sheet of paper, it slides out from under that block, and it looked like the block didn't move at all, or barely moved, right? So there is a speed factor with friction, but the speed doesn't affect actually how much there is. It just affects how long that it has to, in a sense, remain in contact with the two objects. Okay, so if I pull very quickly and I have fairly smooth surfaces, we could achieve something like this. Friction didn't have a long time to act, therefore nothing much happened. We got it out of the way very quickly. But I want to be clear that whether I pull slowly or quickly, the amount of friction is solely based on the two surfaces I have and the normal force between them. Whether I pull slow or fast, that's still the same. It's just as I pull fast, I don't allow much time for friction to act. And then due to Newton's first law, this object was an object at rest. It wanted to stay at rest. Friction was an unbalanced force, but pulling it quickly, it doesn't have much time to act, so the object stays there. So that's a typical demonstration with this kind of stuff. All right, now let's break down the main difference between static and kinetic. Then we'll look at some of their equations in the notes. Okay. So for the first type of friction, static friction, I have underlined in the notes, it's non-sliding friction. Okay. So if I go up and put a force on this object, actually let's take a step back for a second. This object right here, let's go full screen for now. Try to at least. Let's go back to full screen. So this object sitting right here, the only force is acting on is weight downward and its normal force upward. If nothing is trying to move that, there's no friction on it. So if I bring my hand in there and give it the slightest amount of force, it should slide. But it doesn't, because that proves now there's friction. But it's not sliding yet. We call this static friction. If we push on something but it hasn't yet begun to slide, that's known as static friction. Okay? I could prove that by taking something with extremely low friction, which we could make negligible. If I put the tiniest force on this little hovercraft, that little tiny force just made this move. All right? If I turn it off and put that same tiny force on it, this thing's not moving at all. So that must mean it's trying to move when I put a little force on there. So if it's trying to move or trying to slide, let's say, then it's called static friction. And there's actually an inequality for static friction. And move this up a little bit. The reason why there's an inequality is because static friction builds up to a breaking point. All right? If I push a little bit harder, a little bit harder, a little bit harder, eventually this object will break into motion. Right? Now the maximum static friction force between two objects, two surfaces, is an equality, again, only at its maximum. But we could build up to that, so the static friction could be less than that. The static friction will build up, and build up to this point, and that point's the breaking point if I push harder than that. So the formula would be the static frictional force is less than or equal to the mu, the coefficient, that number that's the textures between, and the normal force. Okay. In this case, if this is a 10 Newton object, the normal force is 10 newtons because we're on a flat surface and I'm pushing horizontally, right? Multiplied by the mu, which I don't know. It's a specific value between the surfaces. A lot of times we're either given that or have to calculate that mathematically. All right. So let's say I know this mu value and this normal force. Let's say let's make it simple, 0.5. And if the normal force is 10 newtons, 0.5 times 10, using this formula, is 5, right? 5 newtons. And using it as an equality, it means that that's the maximum static frictional force, 5 newtons. So if I come along with my finger, let's go full screen again here. If I come along with my finger and push with 1 newton, that's not enough to break it, right? It's still not moving, but I'm trying to move it, so there's static friction there. The max static is 5 newtons by the equality. but this is where the less than symbol comes in. It could be less than that too. If I push with 2 newtons, take my word for it, I push a little harder, I'm pushing with 2 newtons now. It shouldn't move still because I'm not breaking it. I'm not breaking what the maximum is. Once I push a little bit harder, a little bit harder, a little bit harder, eventually it breaks into motion. And at that point, once it starts to slide, it's a different style of friction we'll get to in a second here. But I want everybody to understand why this is an inequality, because just simply multiplying these two values gives you the maximum at the breaking point. Anything else, though, if I push less, will create smaller amounts that don't make it move, that are less than that 5 newtons. Okay, so that's a very, very important concept with static friction. So it did break into motion, and now it becomes, once it starts to slide, it becomes kinetic friction. All right, kinetic friction is always an equality. It's equal to the coefficient of kinetic friction times the normal force. All right, and I'll get the difference between UK and US in a second. But there's no like breaking point here. It did break into motion, so that's a moot point now. So kinetic friction formula is still the same two ideas. The mu times the normal force, the coefficient of friction times the normal force, but it's always an equality. So, but here's the deal. Notice I subscript in the notes UK and US. There is a difference there. If we would look up, and you might have to in your textbook during some problems, if you look up in a table of mu values for common surfaces in contact, you will see a different mu static value and mu kinetic value. And you'll notice that the static values for mu, when it's not sliding, are always higher than the kinetic values for mu. So, for example, maybe you look up like a mu value in a table in a textbook, or maybe you experimentally get them too, whatever. Somehow you have a resource where you look them up. And maybe, because this is a wood block and this is a wood table, you would see that for wood on wood static, it might be, let's say, 0.7, okay? But for wood on wood kinetic, it might drop to like maybe 0.5. Okay, the static is always bigger than kinetic in nature. There is an exception to that with some very, very smooth substances like Teflon, but other than those rare cases like that, when you have two surfaces in contact, the mu value, the roughness or smoothness rating, that's usually between 0 and 1, is higher for static cases than for kinetic cases. And physicists and engineers have known that for a long time. So let's discuss this idea and this known thing for something that eventually over time became engineered in pretty much all vehicles nowadays. And that's braking systems. All right, friction is very important to your braking system. When your wheel is rolling and decides to stop, there's friction between the tire and the road that directly causes you to stop. Because obviously if there's ice on the road, right, bringing the paper in, that's ice, you're going to slide more because that lowers your mu value. But there's a bigger internal part of the friction in the mechanics of your braking system in the first place. And I know not everybody out there probably knows every part of a car, and some of you might, but just to make it simple, when you hit your brake pedal in your vehicle, what it does is typically hydraulically leads to your brake pad, which clamps onto something on your wheel called the rotor. And the rotor looks like a disc. It's a metal disc. If they're newer, they will look very shiny. If you ever happen to be cleaning your car or just looking at your tire of your car, on most vehicles, behind the rim of your vehicle, you could see a shiny disc. If they're kind of old, they might be a little rusty. And you could see a brake clamp that's like a caliper, it's called, that's about this, if this is to scale, if this was the rotor, my hand's about the size of caliper or the brake pad right here. And when your wheel's rolling, the brake pad, you press the brake and it grabs the rotor, and the rotor's attached to your wheels. The wheels have tires which are touching the road, and all that friction stops everything. But remember what we said a moment ago, that minus some rare cases, the static friction U is always greater than kinetic. So that means you're going to get higher, better static frictional values, and therefore quicker stopping distances if you're under static conditions than if you're under kinetics, which is sliding, right? If your mu values are smaller for kinetic, when you lock the brake, when you hit those brakes, if you start sliding, you now have a mu k value between your tire and the road, okay? And it will take longer to stop. Not only that, another bad thing about sliding a vehicle, not only will it take you longer to stop because it's a lower amount of friction under kinetic circumstances, but once you start to slide in a vehicle, you could easily lose control as well. So that's another reason you don't want to be sliding. So, and it's engineers knew this for a long time, but for a long time they didn't have the technological capabilities to implement a system that prevents you from sliding. Now, we all take this for granted because probably for at least the last 30 years, if not more, pretty much all braking systems in cars are called anti-lock brake systems. But let's go back before that. There was a time when if you hit your brake, the brake pad just, if you held in the brake, it just locked onto your rotor. And imagine something moving very fast, a lot of inertia, a lot of mass, right? And all of a sudden the wheels on this big massive object lock up. Because of the inertia and the fact that you're a big car and you're in motion and want to stay in motion, if you would slam on the brakes with non-anti-lock brakes, you will start sliding and leaving skid marks immediately. And it will take you longer to slide and possibly throw you out of control. So, one thing that was often taught back in those days, because this idea was known, there just wasn't a system in a car in place for it, is that if you were coming to a stop, you were to pump the brakes. And that would cause the brake pads, by pumping your foot, to grab it, let go, grab it, let go, grab it, let go. And that would allow the wheels to continue to turn while you were stopping, and they wouldn't slide. They'd be in static contact. They'd be rolling over them, but in static contact, not sliding contact. Okay? And this is more safe. But here's the problem. When do people usually slam on have to stop quickly? During maybe an accident or something jumps out in front of them, right? Now, it's easy to tell somebody to pump the brakes in a situation like that. It's hard to be the person that's like, oh, I'm about to wreck. I'm going to pump my brakes casually. Most people would panic, slam on the brakes, lock up, and go sliding out of control and take longer to stop. So eventually, engineers created anti-lock brake systems. So now if you press on your brake, and if you press on it really gently, you even feel the pumping motion back on your foot on the pedal as you brake. And basically, if you hold the brake in, it pumps for you. Okay? Now, this helps reduce the chances of not sliding. Okay? It's not perfect, though. If you're going really fast and still slam on anti-lock brakes during the periods of it basically pumping itself, it could still momentarily lock up. It prevents you from sliding. It doesn't guarantee it, but it's much better than what it was. And the main reason why is it comes down to that mu value. In either case, whether you have anti-lock brakes or non-anti-lock brakes, your car and you in it have a certain amount of mass pressing against that road. So the normal force is a constant in both cases. All right? Because the weight of the object on a flat road would create the normal force it presses back, right? And the textures are also a constant, unless you get into ice or something like that, but let's say the same road for this circumstance. So those are constant, but what we can change and manipulate is if we slide or don't slide. That'll change the kind and amount of friction. And speaking of that, one more car example of what people used to do a lot back in the day, many years ago. A lot of cars were rear wheel drive, 30, 40 years ago. And that caused them to not be so good in slick weather, especially snow. So one thing people would do to help their rear wheel drive get more friction would be, I'm just making a video. No, thanks. Sorry guys. Okay, anyways, one thing that they would do to help their tires gain more friction is put sandbags above the wheel wells in their trunks, and that would create a bigger downward weight of force on top of the wheels, upping the normal force, pushing the tires in the road closer together. So that's another example of something that applies to this that maybe we've heard of before. But with front wheel drive, the engine is typically over the tires now, and there's a lot of weight over them, and that's not possible to put there nor necessary really. I'm going to flip back to the notes here for a second. And rolling friction, I said we'd speak of a little bit. So very quickly, when something is rolling, especially a hard surface on another surface, if it's rolling without like peeling out or slipping basically, if it's just rolling along normally, and especially if the two surfaces are hard surfaces in contact, you get extremely low friction for rolling friction. That's why like trains use steel wheels and steel rails, because steel is very hard, and two pieces of steel rolling over top of each other creates really small values from you. I'm talking really close to zero, like 0.000 values. Okay, and that's better for the fuel mileage of a train if there's less resistance in the rolling. Now, of course, on tires on cars, they're not locked to rails. They're not locked to the road like rails, right? So you can't, and the roads are asphalt, not steel. And you have to have traction that you stay on them and don't fly off. So rubber is used because it creates more friction, more rolling friction, and helps you grip to stay on. So in that case, you don't want it to be too low because you don't want to fly off the road. But something like a rail system or on a roller coaster, steel on steel is great because it allows for the least resistance, but it's locked into the rail. So that's a little bit different than us driving our vehicles. We're not locked onto the road, so we need that more friction like with rubber tires. But other than that, we're not going to speak much of rolling friction. Might be in class here or there, mention it a couple more times, but it's more about right now sliding versus non-sliding with static and kinetic friction. So that's the concept behind all this stuff. Hopefully we have a decent grasp of that. I'm going to make a separate video going over the examples and post those, and you'll be ready to take on some friction problems.